This video is about Bernoulli variables and the geometric distribution. So Bernoulli variables are the basis for two different distributions that we'll study. One is the geometric, which we'll do in this video. One is the binomial, which we'll get to later in these slides. A Bernoulli variable is just a discrete random variable whose only possible values are 0 and 1. So it's kind of the simplest possible random variable. There's only those two possibilities. All right. Here are some examples you can see. Very many things, many probability experiments, we could just define success to be some subset of the sample space and call that x equals 1, and everything else is x equals 0. So it could be heads if we flip a coin. It could be an item passing quality control in manufacturing. It could be you pick someone at random and that person is employed, right? And then the opposite is x equals 0. The jargon here is that each iteration of such an experiment is called a trial. So you could, flip a coin over and over and over, and the different trials, you get x equals 1 on some, x equals 0 on others. You could survey different people, some employed, some not employed, etc. So each iteration is a trial, and the trials are either success, that's just, sort of attached to the x equals 1 case, or failure if x equals 0. Right, this has a very simple PMF here. Again, x can only be 0 or 1, and the 1 case occurs with probability lowercase p, and so the failure case occurs with probability 1 minus p. The mean of a Bernoulli variable is just lowercase p, the probability of success. This is the variance. This is the standard deviation. The mean, let's go ahead, just derive that. Only takes a moment. So remember, what we're doing for an expected value is we're taking a weighted average of all the possible values of x, where the weights are probabilities or PMF values. So x can be 0 with probability 1 minus p, or it can be 1 with probability p, and you can see that reduces just to lowercase p, the probability of success. All right, so that's sort of a complete description of Bernoulli variables. They're not very complicated, but we are usually, if we're dealing with Bernoulli variables, we're often thinking about multiple iterations or multiple trials of the underlying process, okay? And so one of the distributions that comes out of this idea of repeated Bernoulli trials is the geometric distribution. The geometric describes how many trials we need to observe the first success. Those trials need to be independent and identical. So the outcome, like flipping a coin is a good example, the outcome of one coin flip doesn't influence the outcomes of other coin flips. Right? They're independent processes, and the odds are the same on every single coin flip. So that's a classic sort of trial. Here, the example we'll use is how many times would you have to roll a 6-sided die before a 6 appears? So this sets up for a Bernoulli trial with probability of success 1 over 6 and probability of failure 5 over 6. Remember here that often we will have a situation where the sample space may be quite large, but we're willing to say some subset of this sample space is success and some subset is failure. So in this case, the sample space has these 6 equally likely outcomes. And we say this is the success case. And everything else is the failure case that'll map to x equals 0. Okay, so it doesn't have to be that the underlying process itself is binary, but we're willing to define some dichotomy on the outcomes in the sample space and say that, again, some subset counts as success. Here that's rolling a 6, and everything else is failure. All right. Now, how do we think about probabilities here for the geometric distribution? Well, let's think first about what's the probability that it only takes us one roll of this die to get a success. So that happens with probability 1 over 6. There's a 1 in 6 chance that the first time we roll it, we get a 6. Simple enough. What's the probability it takes us 2 rolls to get a success? Well, if it takes us 2 rolls to get our first success, then we know there was failure on the first roll. Failure happens here with probability 5 over 6. Success happens with probability 1 over 6 on the second roll, and all the rolls are independent. So we can just multiply probabilities in order to get the probability that x is equal to 2. All right, now, what if x is equal to 3? What that means is that our sequence was failure, failure, success. And the probability of that sequence occurring is 1 minus p times 1 minus p times p. So 5 over 6 quantity squared times 1 over 6. And hopefully by now you can see the pattern. Every additional number of trials it takes to get the first success, the probability of needing that many trials, we're just going to sort of pre-multiply this expression by 1 minus p. All right, so that leads to the following PMF for the geometric distribution. The probability it takes us in trials exactly to get our first success is this. We need n minus 1 failures to happen first. So we have 1 minus p raised to that n minus 1 power, and then we need success on the last trial. And notice that there is positive probability on needing any number of trials. It is not guaranteed that we will get a 6 within the first 20 rolls of a die, or 200 rolls of a die, or 2 million rolls of a die, right? It would be shocking in a way if we didn't get a 6 within the first thousands of rolls of a die, right? But it's not, the probability is not 1 that that will happen, okay? The CDF looks like this. Again, capital F. This is the CDF, 1 minus quantity, 1 minus p raised to the power n. And we won't show it, or we won't derive it, but the mean of the geometric distribution is 1 over p. So on average, how many rolls does it take you to get a 6? 1 over quantity, 1 over 6, or 6 rolls. All right, so that's the geometric distribution.